Welcome to the deep dive. Today we are tackling a monumental stack of material. This is the absolute foundational knowledge you need for core Java proficiency. We've synthesized a ton of sources to get to the heart of it.
Exactly. This deep dive is all about building that definitive mental model of Java. We're not just, reading definitions. We're trying to extract the essential connections, the trade-offs, the things that really make the knowledge stick.
Right. Our mission is to break down the fundamentals, the execution environment, its object-oriented backbone, and, maybe most importantly, the modern features from Java 8 onwards. Okay, let's unpack this, starting right at the beginning. What is Java, really? And how does it even run?
Well, the textbook answer is that it's a high-level object-oriented language. But its real power, the thing that made it so huge, is platform independence. That was revolutionary at the time.
And that mechanism, the thing that makes it independent, is the key takeaway here. It's bytecode.
Yeah.
When you compile Java, it's not turning into machine code for your Mac or your Windows machine. It becomes this intermediate thing, bytecode, which then gets interpreted.
And that's where the ecosystem comes in.
Yeah.
You absolutely have to know the difference between three key components: the JVM, the JRE, and the JDK. People mix these up all the time.
Yeah, they do. Let's think of it like a chain. The JVM, the Java Virtual Machine, that's the engine. It's an abstract machine that takes the bytecode and makes it run on whatever specific operating system you're on.
Right, and then you have the JRE, the Java Runtime Environment. That's the software package you actually install to run a Java application. It includes that JVM, plus all the necessary libraries.
And finally, for developers, there's the big one, the JDK, the Java Development Kit. It has everything, the JRE, which is the JVM, and on top of that, all the tools, the compiler, the debugger, everything you need to actually write the code.
That hierarchy is absolutely key. JDK contains the JRE, which contains the JVM. Once you get that, the whole build and run process makes sense. So, moving on from how it runs, let's talk about its philosophy. Object-oriented programming, OOP. This isn't just a list of features, it's how you're supposed to think when building systems in Java.
And you have the 4 pillars: encapsulation, inheritance, polymorphism, and abstraction. These are the bedrock.
But let's go past the definitions. How do they actually work in practice?
Okay, so take encapsulation. It's not just about bundling data and methods. In Java, it's really enforced using access modifiers. You make your data fields private, and then you only expose them through, public getter and setter methods.
You're protecting the object's internal state. You can't just mess with it from the outside.
Exactly. Then you have inheritance, which is all about code reuse. It creates that is a relationship. A car is a vehicle. It inherits the properties of a vehicle.
In polymorphism, which we'll definitely circle back to, lets one thing take many forms.
Yeah.
And then abstraction. This one feels really foundational for good design. It is. It's all about hiding the messy details. You show only what's necessary, and you do that mainly with abstract classes and interfaces.
Okay, so here's the classic gotcha question. If Java is so focused on these feelers, why isn't it considered a purely object-oriented language?
Yeah, it's because of the primitives. Things like int, char, boolean. For performance reasons, they exist outside the object hierarchy. They aren't objects.
And since not everything is an object, it can't be called pure, unlike, say, Smalltalk.
Exactly.
Okay, let's zoom back in on the JVM for a second and talk about memory. This is critical for debugging. The JVM carves up memory into a few key areas: the heap, the stack, and the method area.
Right. The method area holds all your class-level data, static stuff.
Yeah.
The stack is super fast. That's for your local variables and keeping track of which method called which. But the big one everyone talks about is the heap.
The heap is where every single object instance lives. And since that memory is dynamic, it has to be managed. Which brings us to
Garbage collection, GC. It's one of Java's biggest selling points. It's automatic. It runs in the background, finds objects that aren't being used anymore, and frees up that memory.
preventing a whole class of memory leaks that you'd have to handle manually in other languages.
A huge, huge benefit.
But before an object gets garbage collected, it has to be created. That's what constructors are for, right? They're like special methods that initialize an object when you create it.
Yep, they ensure an object starts its life in a valid state. Now, you mentioned we'd circle back to polymorphism. Let's do that, because the distinction between overloading and overriding is critical.
Method overloading. This is the first one. It's also known as compile time polymorphism.
Right. It just means you can have multiple methods in the same class with the same name, as long as their parameters, their signatures are different. The compiler knows exactly which one you mean before the code even runs.
It's all decided at compile time. But method overriding is different. That's runtime polymorphism.
A much more dynamic concept. This is when a subclass provides its own version of a method that it inherited from a parent class. The JVM doesn't decide which version to run until the program is actually executing.
And that lets you get really flexible, dynamic behavior based on the actual type of the object.
Precisely. And let's clear up one more distinction while we're on design. Abstract classes versus interfaces. Both are used for abstraction.
Right. An abstract class can provide a partial implementation. It can have some methods with code and some that are left abstract for subclasses to define. It's for an ISO relationship.
Whereas an interface is traditionally about full abstraction. It's just a contract. It defines what a class can do, but not how. It creates a can-do relationship, and a class can implement many interfaces.
Okay, this is where it gets really, really interesting for me. Let's talk about data, specifically strings and the whole idea of identity.
The famous string immutability.
Exactly. The standard string class in Java is immutable. Once you create a string object, that's it. You can't change it. If you think you're changing it, you're actually just creating a whole new object.
And people always ask why. It seems inefficient.
Oh.
But it's for security, it's for caching, and maybe most importantly, thread safety. An immutable object is inherently thread safe.
But what if you need to change a string a lot?
Then you have options. String Builder is your go-to. It's mutable and it's very fast for a single thread.
And if you have multiple threads,
Then you need String Buffer. It's also mutable, but all of its methods are synchronized. That makes it thread safe, but you do take a bit of a performance hit for that safety.
another trade-off, speed versus safety. Okay, let's tackle the next big hurdle, the equality contract. This is the difference between ED and EXT DAQULs.
A concept that trips up so many people. If you use the double equals, you are checking for reference equality. Are these two variables pointing to the exact same spot in memory?
And the equals method is for value equality. Do these two objects, which might be in different memory locations, actually contain the same data?
Right, and for your own custom objects, you have to write that equals method yourself. But it doesn't work in isolation. It's part of a contract with another method, hash code.
This is the non-negotiable part.
Absolutely. The contract is, if two objects are equal according to your equals method, they must return the same integer from hash code.
And why is that so critical for something like a hash map?
Because a hash map uses the hash code to figure out where to store the object. It uses it to find the right bucket. If two equal objects gave you different hash codes, you could put something in the map.
But you'd never find it again because you'd look in the wrong place. Your map would be fundamentally broken.
Broken. Exactly.
Okay, quick aside. We mentioned primitives earlier, like int. But collections like hashmap only work with objects. How does that work?
That's the job of wrapper classes.
Yeah.
Integer for int, double for double, and so on. They let us treat primitives like objects.
And the conversion process is called autoboxing, going from primitive to object, and unboxing is coming back the other way. It's mostly automatic now.
Just some syntactic sugar to make life easier. So that brings us to the collection framework itself. At the top, you have a few core interfaces.
List, set, queue, and map.
And they each have their own rules. A list, like an array list, keeps things in order and allows duplicates. A set, like hash set, is all about uniqueness. No duplicates allowed. And a map, like hash map, stores key value pairs.
And here's another classic comparison, hashmap versus hash table, another concurrency question.
Yep, hash map is what you'll use 99% of the time. It's non-synchronized, so it's faster. Hash table is an older legacy class. It is synchronized, but it's slow because it locks the entire map for every single operation.
Which is a huge bottleneck.
Yeah.
So what's the modern thread-safe solution?
The concurrent hash map, it's brilliant. It achieves thread safety without locking the whole map. It only locks the specific segment or bucket that's being modified, so multiple threads can work on different parts of the map at the same time.
Much, much more performant. Okay, let's shift gears now to control flow, permissions, and exceptions. The mechanics of a running application.
Starting with access control, you have 4 modifiers: private, protected, public, and the one with no keyword, default.
And this all ties back to encapsulation, right? Private is the most restrictive, only inside the class. Public is the least visible everywhere.
Exactly. And then you have the famous 3 Fs, final, finally, and finalize. They sound alike, but they do totally different things.
Let's break them down. Final is a modifier.
Right. It's about preventing change. A final class can't be extended. A final method can't be overridden. A final variable can't be reassigned. It's about immutability.
Okay. Finally is part of a try-catch block for exception handling.
Yes, and the code in the finally block is guaranteed to run, no matter what. Whether an exception was thrown, caught, or not, it's for cleanup. closing files, database connections, that kind of thing.
And the last one, finalize.
Finalize is a method that the garbage collector calls before it reclaims an object. But its use is strongly, strongly discouraged now. It's unpredictable, can cause performance problems. Just avoid it.
Good to know. Okay, speaking of exceptions, there's a big distinction between checked and unchecked exceptions.
There is. Checked exceptions are for things outside your program's control. A file is missing, a network connection drops. The compiler forces you to handle these, either with a try-catch or by declaring that your method throws it.
You have to acknowledge them. But unchecked exceptions.
Those are basically bugs in your code. A null pointer exception, an array index out off bounds exception. They're your fault, so the compiler doesn't force you to catch them, although sometimes it's a good idea too.
Got it. Now what about concurrency, multi-threading?
Essential for modern hardware. The goal is to run multiple tasks at the same time to make your application faster and more responsive.
But it comes with a whole host of new problems to think about. You have the thread lifecycle, you need synchronization to protect shared data.
And you have to avoid scary things like deadlocks, where threads are stuck waiting for each other forever, and race conditions, where the result depends on which thread gets there first. It's complex.
Which is why we now have things like the executor service, right? To abstract away a lot of that complexity.
Exactly. It's a much higher level, safer way to manage threads.
And this feels like a good transition to the really big shift in the language. Java 8. This wasn't just an update, it was almost a new way of thinking about Java.
It absolutely was. It brought in a huge dose of functional programming. The biggest feature, of course, being Lambda expressions.
Which are basically just a short, clean way to write an anonymous function.
Right. And they work with functional interfaces, which are simply interfaces with one single abstract method. Lambda's made so much code, especially around collections, way more readable.
And that leads directly to streams.
Yeah, the Stream API. It's a declarative way to process data. Instead of writing these messy for loops, you can chain operations together.
Yeah.
Filter this, map that, collect the results. You say what you want done, not how to do it.
And finally, a solution to a problem that has plagued Java developers forever. The null pointer exception. The optional class.
A beautiful, elegant solution. Instead of returning null, you return an optional that might or might not contain a value. It forces the developer to explicitly deal with the not there case, which prevents so many bugs.
All right, let's bring it home. This last section is about how Java talks to the outside world, persistence, databases, and how to structure your code with design patterns.
For persistence, the classic mechanism is serialization. You convert an object state into a stream of bytes.
So you can save it to a file or send it over a network, and then deserialization is just bringing it back.
Correct. And if there's a field inside your object you don't want to save, like a password or a temporary value, you mark it with the transient keyword.
Simple enough. For databases, the foundational API is JDBC, the Java Database Connectivity.
And the steps are pretty standard. Load the driver, get a connection, create a statement, run your query, process the results, and, critically, always close your resources.
Preferably with a try with resources block so it happens automatically.
Absolutely. And finally, to show you know how to build robust, scalable applications, you need to know some common design patterns.
Like the singleton, which ensures you only ever have one instance of a class.
Right. Useful for things like a logger. But you have to be careful with it. It can make testing harder. Then there are creational patterns like the factory and the builder.
Factory helps you create objects without specifying the exact class, which is great for flexibility. And builder is amazing for creating complex objects with lots of optional parts.
And we can't forget behavioral patterns, like the observer pattern. It's a way to let multiple objects get notified when something they're watching changes. It's the foundation of a lot of event-driven systems.
So, what does this all mean? We've gone from the JVM and bytecode all the way up to high-level design patterns. This is really the map of the core language.
It is. We covered an incredible amount of ground. From that crucial equals and hashcode contract to the whole new world that Java 8 opened up, you now really have the essential nuggets for Java fundamentals.
And that raises a really interesting question for you to take away from this. We talk about trade-offs a lot. We contrasted the fast single-threaded string builder with the complex concurrent hash map. So as you go out and design systems, what stands out to you as the most challenging trade-off to manage? Optimizing the single-threaded performance of one specific component, or guaranteeing complex high-speed thread safety across your entire application.
Wrestling with those kinds of fundamental design choices. That's where real expertise is built.
That's it for this deep dive.